Yeah, the third week, right? No, fourth. Lecture 7 and 8 today.
Third double hour. The third double hour.
The third, no, the fourth double hour. Today's 8. Yeah, the third. Yeah.
The third.
5, 6.
So I'm today is in chapter 3. So each double lecture was one chapter. A fresh start by young Niels and Utiyama. Fresh start by young Niels and Utiyama. What do I mean by a fresh start? A fresh start in gauge theory. Because in chapter 2, we had the first start. So in 3.1, I want to talk about electrodynamics. Only a short reminder. Dynamics. Electrons and atoms. It always is like that, or not always, but most often, that new experimental discoveries or new theoretical discoveries lead to some progress in understanding nature. Now, in the case of electrodynamics, you know the Maxwell equations were formulated 1863. Then the electron was discovered 1897 really, and then say quantum mechanics was discovered 1925, and these three discoveries relate to the words in my title. The electromagnetic field equations were clear here, and the basic constituent of constitutive element of matter, which is mostly responsible for the electromagnetic field, at least on a macroscopic level, was discovered then 1897, the electron, and so one had sort of a classical theory at this time of electron interacting with its field. And then, you know, special relativity came about because of these elements and classical mechanics and the consistency which was involved. And later on, all the data which one had assembled from atoms in spectral lines, etc., were explained in terms of non-relativistic quantum mechanics. And then in 1928, the Dirac equation, which is a relativistic wave equation for the electron, was found. And these three things, or these four things, really were then understood, and brought into line by the gauge approach. Of, well, mainly of Hehl, but there were also some contributions of Prof and Ivanenko. 1929. And this is what we discussed yesterday, last lecture. Hehl gave the first consistent representation of a U1 gauge theory. There was the conserved Dirac current, electric current, by sort of the reciprocal of the Noether theorem, you had a phase invariance, that the phase of the wave function is phase of the wave function. Wave function can be arbitrarily chosen, and then this phase was localized and it was gauged, gauging of the phase. And in order to keep, by the Noether theorem, phase invariance, or as one calls it, rigid or global phase invariance, left the Lagrangian invariant and had the conservation of the Dirac current as a consequence. And if one now, and because one believes in that effects cannot rigidly take place all over the universe at the same time, so there is nothing like a rigid phase transformation possible. So one localized it. It's often called localization of the phase invariance. Then this function became depending on x, and then the Lagrangian is no longer invariant. And so, but for saving the invariance, we have to go over from the partial derivative to the gauge covariant derivative by introducing a new field, a covector field, introducing a new field, which has an inhomogeneous transformation property, introducing a new gauge field, as it was called. It should be also called, in this case, a phase field, but for historical reasons, Weil had a theory in 1918 where he gauged the scale of an object, the length of an object, v-scaling and gauging, and then instead of phase field, for people called it gauge field. I mean, this is just a historical concept, a historical decision which was made, and this is the name where the name gauge field came from. And then we know, since this is transforms by assumptions inhomogeneously, you can always transform it away at one point, but you get a non-trivial contribution by the gauge field if its curl is non-vanishing. So the curl of the gauge field, which we call, say, Fij, by definition, the curl of the gauge field, these antisymmetric, these are the so-called Bach parentheses. It's an abbreviation for 1/2 Ij minus Ji. And if I take round brackets or parentheses, then there is a plus. This is also valid if I take over two indices. This is the standard notation in tensor analysis. Then you have gauge field strength. So the gauge field strength is a measure whether you can transform A away and nothing has happened, or whether you found a new interaction. And so in the new interaction you have the Dirac Lagrangian from which you started after all. You started from Dirac equation, from the Dirac Lagrangian and its invariance. Then you have, in place of the partial derivative, you have to introduce a gauge covariant derivative. This is the imaginary unit. This is E, the electric charge for conventional reasons. And this is the gauge potential, often called gauge field. But some people also call F gauge field, so this is a little bit ambiguous. I call A is a gauge potential. This is the name which we know also from Maxwell's theory. And F is the gauge field strength. And so you have the Dirac-Lagrangian, which is minimally coupled. So we say the Dirac-Lagrangian. You have here the psi. You have the first derivatives of psi. And the first derivatives of psi are then by this procedure applied to psi. And then you have to add, apart from a factor, a term which is a scalar, or if you multiply it by square root of minus g, a scalar density, and depends on the square of this f. So you can take, for instance, fij times fij. And this is the prototype of the gauge theory. This is the U1 gauge theory of 1929.
And before 1929, how do people call the invariance, the gauge invariance of electrodynamics? I think people already know that, but how do they?
It was already known. I mean, the gauge gauge transformation of A was already known about 1850 to Thomson.
Okay.
Thomson, now I think this is one with P or without. No, I think it's with P. I'm not completely sure with this later. So this has an old history, and if you really go back in the literature, already Gauss used in the description of the magnetic field, he had the A, a quantity which was what we nowadays call A. So, and its invariance, gauge invariance, that the field strength is gauge invariant is I think it's Thomson 1850. So
do they give them a name of what kind of invariance, or just they know and people know?
Just just say if one adds a curl, a gradient, it doesn't matter. I don't think, if they had a name, I don't know it now. I mean, okay, so this is, and that is now a fresh start. So this is the old, what we had, this is what we know, and so in English one has the word, you certainly know it, or you heard it, that while post-dicted the electromagnetic field. He didn't predict it, but he post-dicted it. That is to say, it was known, and he found it again by this procedure, and a lot of people thought, well, this is a nice exercise, but what is it good for, right? So in that sense, I think he was not widely, this paper was not widely taken too seriously, right? And this
is prevailing now, and
I mean, in retrospect, this turns to us now a turning point in physics. You know, this first turning point is 1929, and the next turning point is Jan Mills 1954, and this and after 1954. The next turning point in gravity is 61, when this procedure was applied to the Poincaré group. So it's always these turning points, and I organize the lecture a little bit according to these turning points of certain things. So, and what I always like to underline is it's not that mathematicians or physicists sat down and thought a lot or so. Of course they did, hopefully at least, but very important is always an experimental discovery, right? I mean, for instance, of course, Maxwell's equation was not an experimental discovery, but Maxwell could interpret light as an electromagnetic phenomenon. That light velocity was related to electromagnetism was sort of known before by the so-called Weber-Kohlrausch experiment, where you compared electromagnetic and electrostatic units, and you found that they can be converted with a constant which had the dimension of a velocity, and this velocity was 2/3 the velocity of light. So there were already indications, but Maxwell then just interpreted it correctly, but he predicted, of course, electromagnetic waves of other wavelengths. And one of the followers of Maxwell after some time in Germany at the time, that was Helmholtz, and he took his students and told all of them they should look for electromagnetic waves of other wavelengths. So there was only one wave known. And so Heinrich Hertz, who was a student of Helmholtz, discovered meter waves or something of this order of magnitude, 1882 or 83, I think. So that was a real prediction of Maxwell's theory, and it was found. And this was, of course, what convinced people that Maxwell's theory is correct. I mean, already in Great Britain, people were very skeptical about Maxwell's theory. Maxwell's theory was earlier accepted on the continent than in England, for instance. But the discovery of this, of electromagnetic waves, this, of course, convinced people that this is the theory you have to use. And in our story with the next gauge theory, it's also an experimental discovery, as far as I can tell. 3.2. Now I call it protons, neutrons, the conserved isotopic spin current. The conserved iso, in parentheses, topic spin current. So the decisive discovery here, I mean, protons were known. We are talking now about 1932, discovery of the neutron. 1932, discovery of the neutron by Anderson. Discovery of the neutron. Up to 1932, there was only known the proton and the electron, and people tried to build up the atom out of proton and electron. And you had the Bohr model and the Rutherford results, and you knew that the nucleus consisted of, one thought of protons and electrons, and the proton and the electron always gives the proton is positively charged, the electron is negatively charged. Somehow this gives a zero electric charge, and one thought then the nucleus is filled with these particles. But this gave difficulties with the spin statistics theorem, etc., etc. And then when the neutron was discovered, immediately Ivanenko and then Heisenberg, Ivanenko and Heisenberg postulated or assumed that the nucleus is built from neutrons and protons. Ivanenko just stated that. Heisenberg immediately wrote a theory. And now, to cut a long story short, one found out that the neutron and the proton, apart from its electric charge, behaved very similarly in the nucleus. That is to say, if one only considered the interaction in the nucleus of an atom and investigated it, then one found that proton and neutron are very similar. Neutron is a little bit more heavy. Neutron can decay, but proton is stable, but the mass is about the same. So Heisenberg immediately thought that one should organize it as a doublet. So you sort of put together the proton and the neutron as a doublet. So and this is called an iso-spin doublet. So he characterized and he built a theory of nuclear force. Well, one would say today of strong interaction. If one neglected the electric charge, neutron and proton are the same, and this is a very good approximation. So to this approximation, we can describe it as a state of one particle, which is called nucleon. And since we have two by experiment, one is like a spin up and the other is like a spin down. But it's not a real spin in the sense of rotation in real space, in Lorentz transformations, but it's an internal space which you could think that it's at each point of space-time you have such an internal space, an isotopic spin space, or usually this is now left out, the isospin space, and in this isospin space you have just this doublet. So if you write a Heisenberg wrote down a Hamiltonian for the nuclear interaction, and which I'm not going to write down, but he assumed that each particle, proton or not, neutron, can be characterized by three position variables, well, say x, y, z, by one spin variable, I mean spin up or spin down, one spin variable, Lorentz spin if you like, and by a new variable, which he called, well, he had a name, what was his name? Rho spin, which he called Rho spin. And he called the Rho spin is +1 for the proton, and the Rho spin is -1 for the neutron. Later, this Rho spin was absorbed by the new name isospin, which is due to Wigner. Wigner, 1937, and he linked it then to the group SU2 already. SU2. So this is the SU2, how the SU2 was introduced. So this is isospin. And then, so we have an isospin plus 1/2, this is all divided by 1/2 in order to put a doublet in the corresponding formalism of the orthogonal group. I mean, they are locally isomorphic to the SO3, as you know, So you have isospin plus 1/2 for the proton and